Hi everyone. Thanks for joining this presentation today. First, it is Kerim. I am Director of Consultancy at NSPEC. Currently, I am leading a power system studies team at NSPEC, which is specialized in power system studies, harmonic filter design, reactive power compensator design, and some over voltage mitigation design solutions. And today I will be talking about ensuring harmonic compliance for battery energy storage systems. I will mainly focusing on a real site case study. Basically, I will be demonstrating the results without harmonic filter and with designed, manufactured, and commissioned a harmonic filter for a real 33 kV connected 50 megawatt best site in the UK. Before starting my presentation, I would like to share my agenda. I will be starting with a quick introduction about NSPEC. Following this, I will be explaining key understanding from this real site case study. And then I will be detailing the grid compliance process, including harmonic model validation based upon actual site measurement, then harmonic filter design, manufacturing process, and then I will be demonstrating harmonic designed, manufactured, and commissioned harmonic filter performance at real site. This is based upon actual site measurement. And finally, I will be providing conclusions, and I will be kindly sharing a few recommendations. Yes, about NSPEC. NSPEC has over 25 years experience. Our core expertise is in power quality to provide grid compliance and also to provide grid compliance solution not only for large energy generators but also for large energy users such as industrial sites and data centers. So overall, at NSPEC, we have three main departments, which are consultancy, manufacturing, and site service team. Our consultancy department does do power system studies. We design components, power quality components, and then we prepare all component specifications. Then our manufacturing team manufacture the products. Our site service team do commissioning of the products, and they do post-commissioning surveys to prove the performance of the actual products. NSPEC is a trusted name in the industry. This is based on not only simulation experience, but also actual site experience. And we operate globally. In this section, I will be explaining the key understanding from this case study. Firstly, a client came to us to solve their harmonic non-compliance problem at the site. And this issue was not captured during pre-connection harmonic desktop studies. And everything was fine, everything was green in the original study. And the site has been constructed, energized, and DNO, distribution network operator, they did actual site measurement at site. And unfortunately, they have captured various non-compliances, which are between 14th and 20th order, and also 55th and 65th harmonic orders, which are quite uncommon for most of the drives or for most of the typical loads. In terms of site explanation here, which is a 33 kV BESS project, which is quite typical in the UK, and 33 kV network. 33 kV network, 33 kV connection point is owned by DNO. Then 33 kV network is connected to 13 kilovolt super grid tertiary winding. it means that this tertiary kV system is isolated by transmission system, and the network is heavily reactive. This is one of the reasons the harmonic non-compliances were appeared here significantly. Then, to start harmonic filter design, firstly, we wanted to validate model because these issues were not captured in the original study. So, considering the site has been already energized, we did a site visit and we did various measurements at the site. This is only a few of the measurements what we have done. Basically, our measurement focus on different power output levels, not only maximum export and import power outputs. So from 0 megawatt to 50 megawatt, charging and discharging operation modes were analyzed in detail. Then we also checked LV circuit breakers are open. Especially this mode was to check the impact of inverter self-impedance on the system, tertiary kV system impedance. And as can be seen here, I think my laser is not working. As can be seen here, there were various non-compliances, which are mainly between 14th and 20th order, and also there are a few between 55th and 65th harmonic orders. And this is a picture from our site team. So, what we did, we have done site measurement, and we analyzed data, and we collected all data from site, and we built a site model. So, as can be seen here, they are our inverters, battery inverters, and the battery inverters are connected to tertiary kV networks through 3-winding transformer, and the tertiary kV is connected to 13 kilovolt tertiary winding through 60 MVA grid transformer. And the point of study was at tertiary kV level. Another important parameter here, self-impedance of the inverter. If we do not include this self-impedance of the inverter in our study, we cannot capture the exceedance between 14th and 20th order. So especially this data set is quite important and essential to include in the model for an accurate analysis. We have validated model, then we have started to design passive harmonic filter for this application. For passive filter, harmonic filter, there are various options, but for this particular application, two types were applicable. One of them is second order filter, the other one is C-type filter. Only difference between these two filters are the capacitor here, which is called as auxiliary capacitor, mainly at 50 Hertz. C-type filter ensures very, very minimal losses. Based upon nominal parameters of the filter, there will no losses, but of course in real life the components will have some tolerance and there will be some loss, but the losses of C-type filters are very, very minimal. So the C-type filter ensures a cost-effective design in long term. And C-type filter parameters. I quickly would like to explain here which parameters are important for C-type filters. There are three main parameters: reactive power output of the filter, tuning frequency of the filter, and quality factor of the filter. The right-hand side plots here, we have compared there only two different MVAR size filter. All other parameters are identical, 1 MVAR versus 5 MVAR. When we increase filter MVAR value, we reduce filter impedance value. Generally, it provides better or more mitigation. Left-hand side slide only two different filter solution, two different tuning frequency solution. One of them is fifth order, the other one is seventh order. The fifth order filter provides better mitigation at fifth order. The seventh order filter provides better mitigation at seventh order. And the right-hand side plots, it demonstrates different quality factors. Mainly the red plot, which is a filter, which is a high quality factor filter. And the blue one is a low quality factor filter. Especially for this particular application, the issue was not at a particular harmonic order. It was at various harmonic order, which is between 14 and 20, and also 55th and 65th order harmonics. We didn't, to ensure a cost-effective design, we only wanted to design a single filter should ensure a full compliance. So that's why quality factor of the filter was a quite important parameter for us. Making quality factor lower, yes, it provides generally better mitigation at various harmonics order, but there is a limitation there. We cannot lower down it a lot. When we started to lower down, it can also amplify background impedance. So there is a balance between quality factor, tuning frequency, and reactive power output of the filter. And also, the most important parameter here, knowing actual filter components are quite important. In simulation world, we can design a very good filter. It can be good. It can be very good in the model, but in real world, it may to build that filter physically, it may not be possible. So designing filter considering actual filter parameters are quite important. So we need to consider actual filter parameters as well. Then we have decided that 3.5 MR filter will be an optimal solution for this site. Here we can see resistor, tuning reactor, and capacitors. In this diagram, the right-hand side picture, this is an inner view of the filter. They are main capacitors, auxiliary capacitors, and tuning reactor, and a fifth CT is there. The resistor was external for this application, so we don't have resistor here, but resistor looks like this enclosure. Then the most, especially for a filter designer, the most exciting and stressful part for me was to measure harmonics after installation, because it was our design, it was our product, and it was fully our responsibility. We have done post-connection harmonic measurement, and we can clearly see here filter performance. These orange bars, all harmonics orders here are within the G55 requirements, so now the site is fully compliant. And in this section, I would like to demonstrate how this passive filter works. Mainly, passive filters, they are a parallel resonance to the entire system. They are parallel impedance to the entire system impedance. So our filter impedance is lower than the system impedance, and we are trying to dampen network impedance. If you can see here, this is one issue here, 55th and 65th harmonic order. The other issue was here, 14th and 20th order. These two resonances were damped, and mitigation was ensured at site. Overall, I would like to share a few key conclusions from this real site case study. First of all, even though the site was fully compliant in the G55 pre-connection G55 study report, the actual results were completely different. There were various non-compliances, which are between 14 and 20, and 55th and 65th harmonic orders. Then we also investigated root cause of this issue. The root cause here, the first resonance between 14th and 20th order, it was causing by an interaction between inverter self-impedance and network impedance. So if we do not include inverter self-impedance in the model, there is no way to detect this resonance. So all results will look green in the report, in pre-connection G55 report. Then the other resonance at high order. As I mentioned earlier, this system was dominantly inductive. So reactive part of the system was quite high. And at 33 kV network, our 33 kV cables were quite short. Total length was less than 1 kilometer. And this high frequency resonance was caused by an interaction between cable capacitance and network reactance. So if cable capacitances are not included correctly in the model, there is no way to detect that resonance. So everything will look fine in the report. And I kindly would like to share a few recommendations here. This is mainly based upon our experience so far. Considering we are a consultancy company and manufacturing company, too many clients came us to supply or to solve their harmonic issue. And of course, to design a filter, we had opportunity to review their G55 reports. And sometimes the reports, the way the methodologies may not be okay. They came to us to supply a filter, but when we look at the model, if we model system correctly, filter is not needed there. So it can be also opposite. So accurate modeling is essential for harmonic studies, especially network model, inverter self-impedance, and cables. They are three key parameters for harmonic studies. Then, if these components are not modeled correctly, everything looks okay in the report. When site is energized, if non-compliance is captured at site, to receive a final acceptance from DNO, it takes time, and it means that this is a potential project delays, because nowadays manufacturing and design process takes approximately 40 weeks, and the most importantly, we have experienced that some of the clients, they do not have enough space for harmonic filter footprint. So if it is not planned at early stage, there can be potential project delays later. And especially if system is weak, extra attention is required for harmonic studies. And my last recommendation here, to design a harmonic filter, we shouldn't rely on software simulations only. We should design harmonic filters considering actual or physical component spectrums or component sizes. Sometimes to build a design filter, which is model or simulation software only, it may not be possible to build that filter in real life. So thank you very much. And if there are any questions, I will be happy to answer.